Okay, in this video we're going to talk about arcs and chords of circles. And we're going to start out by going over the circle conjectures, the first three of our circle conjectures, which we've already looked at a little bit. Circle conjecture number one, if two chords in a circle are congruent, then their arcs are congruent. And down here I'm going to draw some pictures that kind of illustrate each one of these conjectures. So for circle conjecture number one, it says if two chords in a circle are congruent, so let me draw two congruent chords here, try to make those look congruent. So if these two chords are congruent, then according to my circle conjecture number one, their arcs are also congruent. So this is the arc of this chord right here, and this is the arc of this chord right here. So this is a picture that illustrates circle conjecture number one. Circle conjecture number two, if a radius or diameter of a circle is perpendicular to a chord, then it bisects the chord and its arc. Okay, well, let me draw a picture of a radius or a diameter. I'm going to draw a radius that is perpendicular to a chord. So let me see, if I draw a chord here that's perpendicular to this radius, it's not a very straight chord. There we go. Here I have a radius that is perpendicular to a chord. So according to this conjecture, it's perpendicular to a chord, then this radius bisects the chord, which means it cuts the chord into two congruent pieces, and it also bisects the arc. So here's the arc of the chord, and that radius also bisects the arc. So there's a picture illustrating circle conjecture number two. Circle conjecture number three, if two chords in a circle are congruent, then they are equidistant from the center. So let's see, two chords that are congruent. So here's a chord here, and let's make it congruent to this chord right here. And here's the center of my circle. Two chords are congruent, they are equidistant from the center. So the distance from the center of the circle is going to be a perpendicular distance. So now, according to circle conjecture number three, if these two chords here are congruent, then they are equidistant from the center. In other words, these distances here are going to be the same. Now, one of the things you find out for these three circle conjectures is that for each one of these, the converse of the conjecture is also true. So, for example, if I happen to have two arcs in a circle that are congruent, then the chords that go with those arcs are also going to be congruent. If I have a radius that bisects a chord and its arc, then I know that it must be perpendicular to that chord. And if I have two chords that are equidistant from the center, then I know those chords must be congruent. So let's take a look at how we might use these conjectures in some example problems. Example number one there. And first it defines what an inscribed polygon is, just a polygon whose vertices lie on a circle. And then it says an equilateral triangle is inscribed in circle P. Draw and label a picture of this triangle and then name all of the congruent minor arcs. Okay, so if I have a triangle, an equilateral triangle inscribed in circle P, then let me draw a circle P here. An equilateral triangle inscribed in it, that means all of its vertices, all the vertices of the triangle are going to lie on the circle. So I want to draw an equilateral triangle with all of its vertices on the circle. And equilateral means that all of my sides of my triangle are congruent, so I'll go ahead and label those congruent sides. And my triangle is triangle JKL, so let me label those here. JKL. All right, so I have equilateral triangle JKL inscribed in circle P. Draw and label the picture of this triangle inscribed in the circle. Name all of the congruent minor arcs. Okay, so I know that all of these sides of the triangle are congruent, and since the triangle is inscribed, notice that each side of the triangle is also a chord of the circle. And according to circle conjecture number one, if chords in a circle are congruent, then their arcs are also congruent, which means that this arc is congruent to this arc, is congruent to this arc. So now I can name all of my congruent minor arcs, arc JK, that's this one, is congruent to arc KL, which is also congruent to arc JL. All right. Example number 2. In circle 0, which I have drawn right here, if segment OH is perpendicular to segment AT, so let me label that, OH perpendicular to AT, all right, and OM is equal to 8, so OM is 8, find the value of AT. So let's see, and this says, hint, look for a right triangle. Oh wait, I have another piece here. OT is equal to 10. So OT is equal to 10. Okay, so now I can see in my picture, I have the length of this segment here, the length of this segment here, and right here I have a right triangle. Let me draw that triangle right here. That's triangle OMT. That's 8, and that's 10. And if I find this value here, let me call that x. If I find that value here, then I should be able to find the length of segment AT. So let me find this value here. Let's see, it's a right triangle. 8 squared plus x squared equals 10 squared. That's going to be 64 plus x squared equals 100. X squared equals 100 minus 64. Okay, so x is equal to 6. Now remember, one of the things I know from circle conjecture number 2 is that if a radius is perpendicular to a chord, then it bisects the chord, which means that this segment is congruent to this segment. Well, I know the length of this segment is 6, which means the length of the whole segment, AT, must be 2 times 6, which is 12. Example number 3. In circle O, segment MN is congruent to segment PQ. So these two chords here are congruent. If OT equals 3x, so here's OT, and OS equals x plus 15, what is the value of x? Okay, well, so here again I can use my circle conjecture number 3, that tells me if two chords in a circle are congruent, they are equidistant from the center. So since I know these two chords are congruent, I know that their distance, that is their perpendicular distance from the center of the circle, those distances are the same, which means that 3x equals x plus 15. Now I have an equation I can solve for x. Subtract x from both sides. 2x equals 15. Divide both sides by 2, and I get x equals 7.5. Now I'm going to skip over this next example in the notes and let you work on that one on your own. And I want to take a look at example number 5. Example number 5, I've actually got the same picture of the circle as I did in example number 3, but I've got some slightly different information, and I'm asked to find something a little bit different. So let's take a look at example 5. In circle O, OT equals OS equals 15. So OT and OS are both equal to 15. Let me mark that. MN equals 7x plus 13. So segment MN, 7x plus 13. So 7x plus 13 is the length of this segment, this chord. And PQ equals 10x minus 8. 10x minus 8 is this chord. Find the length of a radius of circle O. All right, so the first thing that occurs to me is this seems kind of an odd thing to ask for, because when I look at my picture, I don't even have a radius on the picture at all. The picture doesn't include a radius. So that's one thing that kind of occurs to me right off. Second thing that occurs to me is that since I know that this segment is 15 and this segment is 15, I'm essentially being told that these two chords are the same distance from the center, which tells me that these two chords must be congruent. Well, since I know that, and since I have algebraic expressions for both of those, I can set up an equation and I can solve for x. That doesn't really tell me how to find the radius yet, but I figure that probably can't be a bad thing. Let me go ahead and solve for x and see what that might do for me. So 7x plus 13 equals 10x minus 8, since these two chords are congruent. They're equidistant from the center. So now let me see. Let me just solve this for x. If I subtract 7x from both sides, that's going to be 3x minus 8 equals 13. If I add 8 to both sides, that's going to give me 3x equals 21. And so x is equal to 7. Okay, well now I know the value of x. I still don't have a radius in my picture anywhere, although I'm starting to think maybe there might be a good place for me to draw in a radius that might help me to find the length of the radius. While I'm still thinking about that, since I know what x is, I could go ahead and plug it in here to my expressions for these chords, and I could find the lengths of the chords. So let me go ahead and do that. Chord Mn is 7x plus 13. And since I know x is equal to 7, I can go ahead and plug that in and find the length of chord Mn. That's going to be 49 plus 13, which is 62. Okay, so now I know the length of this chord. Both of these chords are congruent, so I know the length of this chord must also be 62. And I recall from my circle conjecture number 2, if a radius is perpendicular to a chord, then it bisects that chord, which means that this piece of the chord is congruent to this piece of the chord. Since the chord is 62, that means this piece must be half of that, which is going to be 31. So now I'm looking at just this piece of the circle right here. I know I'm trying to find a radius. Here I've got this one section here that I know is 15, this one segment here that I know is 31. Well, it occurs to me that if I were to draw in a radius from the center of the circle to this point Q, I would have a right triangle. Here's a right angle right here. And not only is it a right triangle, but it's a right triangle in which I know the length of this side, I know the length of this side, and the hypotenuse is also the radius of my circle, which is what I'm looking for. Now I just need to use the Pythagorean theorem, solve for x, and I'll have my radius. So let's see. 15 squared plus 31 squared equals x squared. 15 squared is 225. 31 squared is 961. That's 1186 equals x squared. And if I take the square root of both sides, then I get x equals 34.44. This technique, this little trick of drawing in a radius on your circle so as to create a right triangle, this is a very, very handy technique, and you're going to be using this a lot in the practice problems that you're going to be working for these types of problems.